Hi everyone, and welcome to this new class in the description of lift and drag, and specifically how that affects, how these forces affect 3D wings. So let's start by defining some concepts, that we will be talking about, 3D effects. Basically we will be talking about the lift distribution around the wing, we will see some couple of topics around wingtip downwash, and also we will discuss different kind of wing configurations. So let's start by defining what is the lift distribution on a wing. Here you have what is known as a sailplane, which is just an airplane without a motor, and you can see the distribution of the lift, as a function of the position at the wing, right? You can see, for instance, that at the tip of the wing it is basically something near zero, and the lift is more or less constant around the wing, but it decreases for those lengths of the wing where the chord is actually smaller. So in general terms, as we saw before, the lift is a function of the surface. So if we describe the lift as function of the wing, as function of the position of the wing, we will see that those parts which have a chord which is bigger, those parts will have also a higher lift. So this is kind of the distribution of a normal wing. Alright, you also see that the fuselage may have some kind of lift. However, as you may understand, the lift of the fuselage is really negligible compared to that of the wing. The wings are there to produce lift, and the fuselage is just, it may produce a bit of lift but not a lot. Also you see that the tail is generating lift on the opposite direction, which is what we discussed in previous classes. So first of all, lift distribution depends on the chord, as we saw. Depending on the length of the chord, we will have more or less lift, and that is basically the main topic which will decide the amount of lift that we have for one length or another. As we also saw, the fuselage may produce some small lift, and the overall 3D lift coefficient, this is quite interesting, is actually smaller than the 2D coefficient, right? So we discussed for an airfoil that this would be the coefficient of lift curve, and it can be seen that the 3D coefficient of lift is actually something a bit smaller. You can see that the increase of the coefficient of lift as a function of the angle of attack is actually a bit smaller, and this is due to basically all the configuration, the 3D configuration, and also due to the downwash which is produced at the wingtips. So what is downwash? Right, the idea of downwash is that some induced drag may appear, and we have to eliminate it. So let's describe it little by little. Air will go from high pressure, to the point of high pressure to low pressure. As in generic terms, in an airfoil, so let's define any kind of length of the wing. What we will have is actually the flow going up and down, with respect to the wing, right? So the wing is actually some kind of surface, some kind of material, which is separating the low pressure on the top and the high pressure on the bottom, And because we have a different pressure on the top and on the bottom, and there's a fixed material in the middle which separates effectively the different pressures, we will actually have the foil being pushed up. So this is the idea again that we discussed before, And as we mentioned, the pressure is related to velocity, and the geometry of the airfoil will actually enhance the velocity on the top, so that we get the maximum lift as possible, right? So as you can see, for all the wing, we will have two separated parts, one at high pressure and one at low pressure, right? So there's no way the wind or the air can move from the upper part to the lower part, or from the lower part to the upper part, because we have the continuity of the wing, so it cannot move on the sides. right? It can only move from front to back. Okay, so what would happen if we were to discuss the wingtip? Okay, so in the case of the wingtip, and in this case I exaggerated this a bit for it to be more clear, okay, we have high pressure at the bottom, right, at the lower part, which is what we discussed, and low pressure on top. So we will have a difference in pressure that this is translated into lift, okay, at any length of the wing. However, at the wingtip, there will be a point, just the literal wingtip, okay, in which you will have almost at the same point high pressure and low pressure, okay. And by definition, what we know is that air will go from high pressure to low pressure, okay. This is just a fluid dynamics definition. The idea of high pressure would have more internal energy, so if the fluid will tend to go from high pressure to low pressure, because low pressure is simply low energy, okay, and anything in thermodynamics comes from high pressure or high energy to low pressure, okay. So the idea is that we will have the fluid trying to move from high pressure to low pressure. As we discussed, in this case, in the case of the wing, this cannot happen unless the fluid actually goes around it, okay? And there will be, in fact, equilibrium of pressures, but after the wing. So the wing is an effective way of separating the low pressure from the high pressure. However, in this point, we will actually have the fluid moving around, okay? So the vortex, okay, some kind of fluid vortex will be created due to the fact that we have in one point different pressures, okay? So there will be some kind of movement of the fluid around the wingtip, which we must avoid, okay? We must avoid this because it basically generates induced drag. An induced drag is just an additional drag which makes the vehicle less optimal, okay, and less efficient in terms of aerodynamic performance, right? So we can see this in this case over here, okay, in this is an A340, an Airbus A340, and you can see this kind of vortex generating, okay, due to the difference of pressure on top and on the bottom, right? You can see it's completely symmetrical with respect to the airplane and the path of the airplane, and it generates on the wingtips, okay? This is just, it generated just when the airplane went through that particular fluid mass, all right? So my question is, how do we solve this, right? So what we do is we actually add wingtips, right? It's quite a simple solution to the problem. And what it does, it just separates the high pressure from the low pressure in this continuum, okay? And therefore we will have the same pressure over here, but we will remain with some difference of pressure, okay, even to the wingtip. And this is the idea of the definition of wingtips, okay? It's just this point, this geometry, this material over here, which is added in order to separate the high pressure from the low pressure. And this, what will allow, is actually to have some lift, which is the difference of pressure, as you know, which is different from zero, okay, even at the wingtip, right? Because if we didn't have any kind of wingtip, this curve would actually move to zero, because the lift is by definition just the difference of pressure. And if we don't have a way to separating the pressure on the bottom and on the top, we will come to lift equal to zero at this point. So the wingtip, what it allows is to actually improve the lift, okay, on the wingtip. This is the wingtip, okay, and this is why it is used very commonly in many kinds of different aircraft. So let's discuss a bit the several types of wing configurations, okay. Probably the most interesting ones are the constant chord wings, okay, which are these ones over here, which will produce a very high downwash, as you can imagine, because all of this surface, all right, will actually be needing some kind of wingtip, all right, in order to avoid the difference in high pressure and low pressure. Okay, so it's important for constant chord to take into account the effect of the downwash, and in fact it is very critical, and induced drag can increase a lot. So it is important to take this into account. Constant chords are therefore easily manufactured, okay, because it's just the same wing at all, at all lengths of the wing. We have the same dimensions of the chord, so it's very easily constructed since we need just the repetition of the same material. Okay. Another very interesting one is the elliptical one, which is actually kind of it can be constructed, of course, but it's kind of the best optimal lift to drag ratio. And this comes from equations. This comes derived mathematically why the elliptical wing configuration is the best one. Okay, but it just comes down to having a very little wingtip, as you can imagine, and also optimizing the amount of lift for each surface. Okay, it's just optimal in terms of aerodynamic performance. However, the main problem of elliptical wing configuration is that it is not easily constructed, as you may if you want to do some kind of intuition, okay, onto how to manufacture this wing, you can imagine that the chord here will actually be very specific length. This one will be very specific length too. This one too. Okay, so you basically need a very detailed construction of the different elements, and of course the optimization of the lift to drag ratio will only be based on a very precise collocation of the different elements, structural elements of the wing. Okay. In general terms, okay, tapered wings, tapered configurations like this one are the most common and in general terms, they are the best, because they provide good performance, not as optimal as the elliptical, but good performance, reasonably good performance, and at the same time, it's pretty easy to manufacture since you have a very specific length, okay, to cover, and it is a bit easier to manufacture than the elliptical one due to the constraints of the geometry, and that's the idea. So in general terms, most of the airplanes tend to go for the tapered. Okay, you can see that there are a lot of different configurations, also different elements. Okay, depending also, you also have to take into account, for instance, the amount of stress that the fuselage will have to withstand with respect to the wing at the wing root. Okay, so at the point where the wing is actually connected to the fuselage, and this is also a design parameter which has to be taken into account. Okay, so sometimes maybe even if the elliptical is the best one, it can be a bit different, or it can be a bit strange how to connect it correctly to the fuselage, okay, the wing. And as I mentioned before, tapered wings are usually the best ones in all terms. Also, it's interesting to note in supersonic flight, hypersonic flight, okay, we may encounter this kind of delta wings, which have different configurations, and these configurations are just optimized for hypersonic fluid dynamics, which kind of work a bit different to the fluid dynamics of supersonic flight. Okay. So these are some examples of wing configurations that you may encounter. Usually, as we saw, we have tapered wings. Okay, this kind of wing, which you can see the root is kind of big. Okay, it's the chord at the root is quite high, it's quite large. Okay, compared to the wing tip, right? And you can also see that there's some kind of wingtip used. Not much. It's quite small, but it may be, in most cases this is enough. So you just need some little element, okay, to provide the difference in pressure, as we saw before. And you can also see that the configuration is optimally, you can see here all the geometry of the structure around this point, the root, okay, which is actually providing the strength required to withstand the different stresses due to the wing, okay, and actually, because you can imagine that the wing is actually providing lift, so this lift will be connected to the fuselage and will actually you will be structurally connected to the fuselage, only on this surface over here, so this surface has to be very, very, it has to withstand a lot of stresses, which is what we discussed before. So this is why sometimes it's just the configuration, this the kind of configuration, this is optimally, there's more surface of contact, like this, okay? And you can also have the flaps and all of that, which we will discuss later. Right, so this would be the most typical configuration. In the Boeing 747 you can see a very similar configuration, in fact, okay? You may notice that in some other photos generally, but the Boeing 747 has a very rigid body, and also the connection between the root, okay, and the fuselage is very strong. And this is a little aircraft where you can see quite similarly it's also a tapered wing, okay, and it's just a bit more uniform, and you can understand that the stresses here are lower because the amount of lift which will be produced by this wing is lower than in this case, okay, because the whole aircraft is just smaller. So this is a bit the commercial part of it. And just to discuss a bit also the wing configurations on other type of aircraft. All right, you have the Spitfire, which was one of the Britain's most legendary aircraft. Okay, it has this very recognizable elliptical wing, which is mainly one of the few aircraft, okay, which used the elliptical wings. And as we saw, it was optimized for lift-to-drag optimization. However, it was kind of difficult to construct effectively and rapidly. This is the Mustang, the P-61 Mustang, if I remember correctly, from the United States. You can see it's just a tapered wing, okay? So as we saw before, it could have some difference in, for instance, in this point, a wingtip would be okay in order to avoid some of the induced drag that we mentioned. This is the first aircraft, I think this is from the Wright brothers. You can see in this case it actually has two wings, okay, and very, very similar to rectangular. All right, even it's quite interesting to note that there's no airfoil either. So the airfoil, as you may remember, was optimized in order to increase the lift to drag ratio. Okay, so in this case there's even no airfoil. You can see that of course the design at that point was not as advanced, okay, as it is today, but it's quite of an interesting aircraft to see, okay, because it has this, apart from the fact that it has two wings, okay, it's also kind of rectangular, you can see it. And this is just the Concorde, which was a delta wing, because, as you may remember, the Concorde was designed to fly at supersonic flights, okay. So this is kind of an overall of the different wing configurations and 3D effects that you need to know in terms of lift and drag. So let's continue to the next class.